Hello everyone, this is Professor Golestane, and this video will teach you how to deal with ICF tables and mole calculations and I already had a video that described the process with solution stoichiometry, and if you watched that video already, you can try to calculate this problem and see if you get the right answers. So I'm going to work with this chemical reaction. The reaction is iron plus oxygen, and it produces iron 3 oxides. So Fe2O3 solid. The states don't really matter in calculations, and we are making the assumption that the reaction goes in completion. So it's like 100% reaction. So let's say that we work with moles this time, and my table is ICF, and initially I put in let's say 5 moles of iron plus 3 moles of oxygen, and this table unit is in moles, and I don't have any iron oxides initially. And you need to fill out every other line of this table, which is the C line, which is change, and the F line, which refers to final. And before you do anything, make sure your reaction is balanced. If I balance this reaction, I put a 2 in front of iron, put a 3/2 in front of oxygen, and that takes care of it. But because we prefer to use whole numbers, multiply everything times 2 and change it into whole numbers. So iron becomes 4 and oxygen just becomes 3 and iron oxide becomes 2. So in my previous video dealing with the ICF table and solution stoichiometry, I explained the use of these factors or multipliers for conversion factors between a particular component of a reaction related to another component. For example, I'm going to review that for you one more time, and I'm going to bring this down a little bit so I have a little space above so you can see. And if I go from iron to oxygen, what would my factor be? So you multiply your given, which is 5, by a ratio to find the amount of oxygen that's required to react with it. And I explained that in the other video. So you multiply your 5, assuming that the 5 completely reacts. What would be the ratio when you're multiplying it by this factor to get the amount of oxygen needed? So your ratio is either 3/4 or 4/3. Please pick a ratio that's less than 1 in this case, because the 4 moles of iron reacts with 3 moles of oxygen, which is less moles. So the 5 moles of given of iron has to be reacting with less mole of oxygen. So I'm going to be expecting to get less than 5 moles of oxygen here. So the only way you can get less than 5 is you multiply by a factor of 3/4. Because if you multiply by 3/4, your ratio is less than 1. If you happen to multiply by 4/3, 4/3 is greater than 1. Any number multiplied by a number greater than 1 will result in a higher number, higher than what you start with. So take out your calculators and let's do this. So if you assume, now this is clearly an excess, I should have said that. This is clearly excess limiting problem because I don't know what's limiting and I have to figure that out first. So if you base your iron as limiting, assuming that's the case, I'm not going to write anything down yet. So I take a calculator and I multiply my 5 times 3 divided by 4. If you assume iron to be limiting, you need 3.75 mole of oxygen. But look, you only have 3 mole of oxygen. So obviously this calculation is useless. Now work the other way around. Start with the oxygen. and figure out, so you're going the other way around. So I'm going to erase this and see if you can come up with the amount of iron this time. So if you start with 3 mole of oxygen, that's how much you have, and you want to find out how many mole of iron you need, you're going from 3 to 4. So you're going to need to have more iron than the 3 moles here of oxygen. Your factor has to be 4/3. So 3 times 4 divided by 3 will give me 4. Notice that my 3 mole of oxygen required 4 mole of iron. So that makes sense. So it's got to have more mole of iron than what you start with in moles of oxygen. So this calculation makes sense. So now I can start to fill out my tables. So your change line, since oxygen is limiting now, and you have more than enough of iron, you need 4 mole of iron, and you have 5 moles, so you have more than enough. So put a -3, because change line, as I mentioned in the other video, has to have negatives and positives. Negative for reactants, positive for products. And these are moles reacted or moles produced. So -3.0 mole of oxygen, because you have all of your oxygen reacted, that's the limiting reactant. And we just calculated -4 mole of iron. And you also need to figure out the product iron oxide and how much you're going to make. So what would that factor be? If you base everything on 3 mole, so this is my limiting, I'm going to erase the other one. If I base everything on the 3 mole, how much iron oxide I'm going to make? Now look at your ratio. This time you're going from 3 to 2. Oops, sorry. Should have picked the other one. So this time I'm going from 3 to 2 moles. 3 mole of oxygen, you're going to get to go to less mole of iron oxide. So you've got to multiply by what factor? 2/3. Your factor is 2/3. So 3 times 2 divided by 3 is 2. So you're going to make 2 mole of iron oxide. That's how you're going to, this is a very quick way of calculating, and this is how you got to do these tables. It's the best way to handle this sort of thing. So, excuse me. So now we are ready to do the final line. Final line, F line, is essentially the initial plus change, and 5 minus 4 is 1. So we go ahead and put 1.0 mole of iron would be left over. So iron is the excess. And we determine that oxygen is limiting, which is 0. 3 minus 3 is 0. Iron trioxide is 0 plus 2, which is 2 moles. There it is. You found that after the reaction, you have 2 mole of iron trioxide. All of your oxygen is reacted to 0 moles left over. And the iron being excess, you have 1 mole of iron left over. So that's how you want to do this one. Let's see if we can do one more problem and pause the video, solve the problem, and I'm going to work with this here. Again, this is not normally a complete reaction, but I'm going to have you assume that it's a complete reaction, and we want to balance the equation first. And we're just going to throw in some numbers, and I'm going to pick some fractional numbers, and this table is going to be in mole, just like the other one. And ICF table. ICF means you're assuming 100% reaction going forward. So we're just going to throw in some numbers. Let's say you are given 12.5 mole of nitrogen with 19.5 mole of hydrogen, and you don't have any mole of ammonia. So complete the table. Pause the video, you know the method that I just went over, and complete the table. So then when you get your answer, start the video again and check your work. So I'm assuming you just did that. You got your answers. And let's do that. So I'm not going to write anything down. I'm just going to use a calculator. So first thing is I base everything on assuming 12.5 mole of nitrogen reacted. So if 12.5 mole of nitrogen is reacted, you're going from 1 mole to 3 mole. So you're going to be needing more mole of hydrogen than 12.5. So you're going to take your 12.5, multiply it by 3 over 1, which is just 3. So you're going to need 37.5. Look, I only have, I'm going to write this down for you, 19.5 mole. So this calculation doesn't get you anywhere. So don't even record anything about it in this table. So let's go ahead and now work with the other chemical. You have 19.5 mole of hydrogen. If all of that reacts, how many mole of nitrogen would you need? This time, you're going in the opposite direction. You're going from 3 to 1. So your factor, you multiply the 19.5 by, would have to be 1/3, because you're going in less mole of nitrogen direction. So 19.5 times 1 divided by 3 is 6.5. It makes perfect sense. So let's go ahead and put down all of my 19.5 mole react, and I'm only going to react 6.5 mole of nitrogen. You have plenty, you have 12.5. So you're good. This is a good calculation. So I found out that my hydrogen is limiting. It completely reacts away. My nitrogen is excess. Now, how much ammonia am I going to make on the product side? Please note you start with positive because product is made. The change line has to be positive for that. And so now my ratio is I'm going from 3 to 2. What do you think the factor is? Higher mole of hydrogen goes to lower mole of ammonia. So you multiply your 19.5 by a factor of 2/3 times 2 divided by 3 equals 13 moles of ammonia are produced here. So let's keep it to 3-6 fixed, so it's 13.0. So now my final line is just addition of initial and change. And as we mentioned, your limiting hydrogen goes to 0. 12.5 minus 6.5 gives me 6.0 moles of nitrogen that's left over at the end of reaction, and 13.0 mole of ammonia is left over. Again, this is a very powerful method in doing stoichiometry calculation of excess limiting and accounting for everything. In the final line, we are determining all the moles, and these tables work in molarity and mole table, or millimoles. In the previous example, I used millimoles. So you can use millimole in this table or use molarity. As I mentioned before, if you use molarity, the only complication is when you mix chemicals of different volumes together or of the same volume, it doesn't matter. You have to account for concentrations initially that's based on a dilution calculation. So you can't just put in the molarities, individual molarities of these chemicals. You have to work with the molarity in the mixed state at time 0, right at the initial point of mixing them. So you have to do that calculation before. Or you can just work with millimole and then divide by the total volume and you get molarities at the end. Again, the trick is to practice with these and watch these videos over and over until you get these ideas. That's it.